Okay, so here's the example that we're going to be using to properly utilize our new wave equation. A wave p is a sound wave traveling with a velocity of 340 meters per second. It maintains a constant angular frequency of pi over 2 per second. The wave has an amplitude of 1.2 meters. Firstly, write down the mathematical description of the wave, and secondly, solve for the value of y given x is 3 over pi when t is 1 over pi seconds. So you can go ahead and try this problem, and then when you're ready, you can come back for the solution. Okay, so a couple of things that we need to get first is that we have to write down all of our information. So we know our wave speed is 340. Again, it's conveniently in SI units. Meters per second. And a constant angular frequency of pi over 2 per second. So angular frequency is pi over 2 per second. And the amplitude is 1.2. So A is just 1.2 meters. So what can we glean from this? Well, we know it's angular frequency, so from that we can just get its normal frequency, use that to get lambda, and then use that to get the wave number. So a lot of sort of intermediate steps here. So we know that omega is 2 pi times f. So pi over 2 is 2 pi f. So again, we're just going to cancel the pi's here. And we get the frequency is 0.25 hertz. So very, very small here. It's not really a sound you can hear, as the human ear can go between 20 hertz and 20 kilohertz, as we'll probably learn actually in the next chapter. But that's the frequency. F is 0.25 hertz. Then because we're given V, we can find lambda. So V is F lambda. So 340, 0.25 lambda. So it's just going to be twice that. Not twice that, 4 times that. So 340 times 4, which is 1360. So lambda is 1360 meters. Sorry, I don't even know why I underlined that. It's not necessarily an answer or anything, but that is indeed our wavelength. And then from that we can just get our wave number k. So it implies that k is just 2 pi over 1360, which is, I'll keep it in terms of pi because our answer, or our required stuff, is actually in terms of pi. So it gets things cancelling. And that's pi over 680. So pi over 680 per sec, or per meter, not per second. It's radians per meter are the units of k, not per seconds. K is in per meter. So if you remember our wave equation, it's y of x comma t is going to be our amplitude times sine of kx minus omega t. And then, because it doesn't tell us anything about the phase shift, let's just assume that the phase shift is 0 just for simplicity. So plus 0 on our phase shift. So we're going to get the amplitude is 1.2. Sine of pi over 680x minus omega, which we know is pi over 2, so pi over 2 t. So that's the mathematical description. Again, I'll just write y of x comma t. Perfect. So now that's part 1. Part 2, y given x is 3 over pi when t is 1 over pi. So y at x is 3 over pi, t is 1 over pi, is 1.2 sine of pi over 680 times 3 over pi, minus pi over 2 times 1 over pi. So we get the pi's cancelling, and then our answer is going to be 1.2 sine of 3 over 680 minus a half. Again, make sure your calculator's in radians here, because we only work in radians when it's to deal with waves, or simple harmonic motion in general. So we'll get y of 3 over pi, 1 over pi, is 1.2, 1.2 sine of 3 over 680 680 minus a half So our y position is minus 0.57. So minus 0.57, and we'll throw in our units of meters. So at minus 0.57 meters, our wave has an x position of 3 over pi after time 1 over pi seconds.